This is video 4 with Euclidean geometry. We're doing theorem 4 now. And for this theorem, it's called angles in the same segment are equal. So when you're dealing with theorem 4, you'll notice a little bit of a bow tie pattern. By that I mean it's kind of like this little bow tie, physical looking bow tie. So what they're saying is that this angle P1 is equal to angle Q1. They want us to prove that these angles are equal. So if it's subtended, if both of them are subtended by AB, they're saying that these two are equal. Okay, so it sometimes looks a little bit similar to this theorem 3. Do you notice how we had O2 and P2 over here? But remember with this one, O2 is double the size of P2. So what you're looking out for is if it lands up on the circumference or the center. So P and Q are both on the circumference. They're being subtended by AB to the circumference. Whereas this one is also subtended by AB, but to the center and the circumference. So if it lands up center and circumference, this will be double the size of that one. But if it's circumference and circumference, then they are equal. So please watch out. If you see this shape, you might be confused between the two theorems. And you go and say that it's equal or it's double when it's actually the other way around. So if it's circumference and center, center will be double the size of the circumference. But if it's AB to circumference and AB to circumference, they will be equal. Okay, now as a matter of fact, to prove this theorem 4, we're actually going to use theorem 3 now that we know that that is true. So what we're going to say is I want you to look at angle P1. Now let's look at the the center over here. O1 and P1, they're both subtended from AB, O1 and P1. So do you agree with me that angle O1 is actually double the size of P1? So it's 2 times P1. And we just learned this. This is angle at center equals 2 angle at circumference. Right. Now the same thing with Q1. So if you look at Q1, O1, what am I saying, Q1? So angle O1, if it relates to Q1, O1 will be 2 times the size of Q1. Remember, this center angle is double the size of that circumference angle. Again, angle at center equals 2 angle at circumference. Alright, so do you now see that 2P1 and 2Q1 are both equal to O1? So therefore, 2P1 must equal to Q1. Okay, we've just shown that. So therefore, because if we just divide both sides by 2, we have P1 equals Q1, and we have proved this theorem. So all that you do here, it's such an easy one to prove. You use your angle at center and 2 angle at circumference from theorem 3. So again, P1 is half the size of O1 and Q1 is half the size of O1. So they must be equal because they both relate to this angle O1. Okay, so that's quite a simple one to prove. I made a star here as well saying cyclic because I just wanted to sort of mention, and I'll explain to you later on more about cyclic quadrilaterals, but the reverse of this is true as well. So in other words, if this AB subtends P and if AB subtends Q, all 4 of these points must lie on the circumference. So in other words, if these two angles are equal, it means A and B is a chord. It means it lands, A and B are on the circumference as well. Now a cyclic quadrilateral, if I were to go and connect these two, so now you have this little quadrilateral. A cyclic quadrilateral means that the opposite angles add up to 180. Now, in every cyclic quadrilateral, all the angles add up to 360, but it's not necessarily true that the opposite angles add up to 180. So that would be properties of a cyclic quadrilateral, as well as all the points. If you're working in a circle, a cyclic quadrilateral would mean that all the points land up on the circumference. Okay. Alright, but we will learn a little bit more about cyclic quadrilaterals. Now, this over here, I'm just going to run through it and explain it, but they are corollaries for theorem 3 and 4, which means that these are true as well. And it's little things that you can remember that will help you when you're answering questions about Euclidean geometry. So, I'm going to put this over here at the bottom. When 2 points on a circumference subtend at an angle, we said these two angles are equal. Now, the same can be true for different places in the circle. So, in other words, let's say this PQ, right? Let's make that orange, is equal to AB. If I subtend an angle from AB, it's angle C, it will be equal to the angle subtended from PQ, R, because the chords are the same length. They are in the same circles. Okay, and that's basically true if you have two different circles, okay, and the chords are equal, so there's your chords that are equal, as well as your arc. Remember, this is your arc. That basically is saying to us that the circles are the same size. They will subtend equal angles. So same, if it's a different circle and the chords are the same as well as the arcs, it will also subtend the same angle. Alright, this one says equal chords or arcs subtend equal angles at the center of the circle. Okay, so now they are saying that not only does this work at the circumference, it also works at the center. So if the arc and the chord is the same, that angle will equal that angle because this arc and that chord is also the same. Okay, chords / arcs are equal if they subtend equal angles at the circumference or the center. So now they're saying the reverse is true. So let's say, for example, they tell you 1 and 2 are equal. You could say, therefore I know AB is equal to PQ. So basically the reverse. Same thing over here. Let's say they tell you C and R are equal. Then you know, okay, PQ is equal to AB. Alright, now this next one is possibly the one you will use the most. It says the diameter of a circle subtends a right angle on the circumference. So in other words, if this is the diameter, AB is the diameter, and you subtend an angle, C, it will be right angled. So this will happen in any circle, no matter how big it is. This is my circle. I make a diameter. It will subtend a right angle there. Okay, it will subtend a right angle here. It will subtend a right angle there. Basically, anywhere on the circumference, if you draw two lines and meets at the circumference, it will be a right angle if it comes from a diameter. Same on this side. If I do this, it will be a right angle. So this particular, the reason, take note of the reason they say angles in a semicircle. Okay, you will use this reason quite often when you are answering questions about Euclidean geometry. So please take special note of this one. Angles in a semicircle. Also for theorem 4, the reason, if you're going to use this theorem, remember we need to know what these reasons are. We call it angles in same segment. Okay, angles in the same segment. I might send you a document with all the theorems, basically what they are and what the reasons are. I think that'll help you in answering questions. Maybe we'll make a little summary at the end of this. Okay, so this one, if you're using theorem 4, you're going to say angles in the same segment. If you use this over here with this with a diameter that makes 90, you're going to say angles in a semicircle. That will be this reason. Okay, now let's do an example and then yeah, we'll end this video and go on to Theorem 6. Okay, so in the diagram below, well actually it's above, I'll copy the question. A, B, and C are points on the circle O. B, C, and D are points on the smaller circle passing through O. Prove that AD equals DC. Okay, so they're saying that A is on this bigger circle. They're saying this O is the center, and B, D, and C fall on this smaller circle. Okay, so basically what they want us to prove is that AD, so I'm going to take my ruler here. Let's color it in. They want us to show that this AD is equal to DC. They want it to be equal to this line over here. Now, this is a triangle, and quite usually when they ask you to prove that two sides of a triangle are equal to each other, a good way to go is proving that it's isosceles. And what do you know about an isosceles triangle? It's that the base angles are equal. So if we can prove that angle A is equal to this whole angle C, then the two sides must be equal, because then it would be an isosceles triangle, correct? So, and I mean, the theorems we've been doing all relate to angles. So let's start playing around with the angles. They've given us that angle A is X. So let's start filling in other angles. And I mean, you've learned a few theorems now, so you can use what you like. But I'm going to move this page around. If we're starting with this angle A, okay, I'm going to turn it like this. Let's look in the big circle now. This is angle A. If I pull these two lines the same from BC to angle O, do you notice that this is that theorem? Angle at the center is twice angle at the circumference. So I'm going to go ahead and write 2x. If that is x, this must be 2x, because the center is double the size of the circumference. Okay, so I know that that is 2x. Now I'll continue playing around. Do you see your little bow tie here? There's a little bow tie looking thing. Something like that. Okay, so it subtends O at the circumference, and it subtends D at the circumference. So please don't now go and think that D is going to be half the size of O, because remember, this is now your little circle. That's a circumference. This O is on the little circle's circumference, and this D is on the little circle's circumference. So this is theorem 4. That means that this O is equal to this D1. So D1 is also going to be 2x. Okay, so now we've got this angle. We'll write all of this afterwards, but we've got this D1 is 2x. Okay, so that maybe makes our life a bit easier, because remember, we're trying to kind of get to this triangle where we can show that A and C are equal. So if you look at this, let's look in the bigger triangle here. This line and this line and this line. This forms an exterior angle. Remember, exterior angle equals the sum of the two interior opposite. Okay, so if A and C plus together gives me 2x, I can calculate what C is. Can you kind of see where this is going? Okay, so let me just make sure this page is still in the shot when I turn it. Okay, all right, so now that I've got a lot of information, I'm going to start writing it down and see what happens. Okay, so the first thing I did was I said angle O1 is equal to 2 times angle A, which equals 2x, because angle at center equals 2 angle at circumference. Are you with me? Okay, the angle at the center, remember, this is the center of the big circle, and A is the circumference of the big circle, so that's theorem 3. So just try and not get confused between center and circumference. This was circumference and circumference of the little circle, so therefore those two were equal. Okay, so now I know that angle O1 is 2x. I've proved that. Now I can go ahead and say angle D1 is equal to 2x as well. Or you can actually, I'm going to write it like this, sorry. Angle D1 equals angle O1, which equals 2x. I feel like you can never write too much information, so rather go the extra step and make sure you get all your marks. So angle D1 is equal to angle O1, which is 2x. So then you're going to say, what was the reason for theorem 4? It was angles in same segment. Are you with me? Angles in same segment. That was your bow ties to do with the circumference. Okay, so then we decided that angle D1 is 2x. We've got that. And lastly, I mentioned that if you have a good look at this, you can see that this is an exterior angle, and these two plus together would give me that exterior angle. Remember, there's many ways to go about it. You could have also looked at the fact that this D2 is on a straight line. So you could have said D2 is equal to 180 minus 2x, and then used sum angles of a triangle equals 180 and worked it out from there. I just think this saves us a step. So we're going to say angle D1 is equal to angle A plus angle C, because angles in a triangle equals 180. So let's go and fill it in. Angle D1 is 2x, angle A is x, and we don't know angle C. So now you can, oh sorry, that must be a plus. We don't know angle C. So if I take my x over, it becomes 2x minus x equals C. 2x minus x is just x. So angle C equals x. So now if this C equals x, we know A equals x. So therefore, angle A equals angle C, which equals x, which we have now proven. You don't have to write any reason for that. So therefore, length AD must equal length DC, because this is an isosceles triangle. Okay, so I'm going to write base angles isosceles triangle are equal, right? Or you can say angles opposite equal signs are equal, so therefore the lines must also be equal. Okay, I hope that makes sense, and I'll get the next video on theorem 5.